This is continuation of the tutorial series on kinematics of mechanisms. Contents of video 6 on 10 will be solving few problems on how to find degree of freedom. Sometimes it is also known as mobility. We'll be considering few standard planar mechanisms and a very few special mechanisms as well. Okay, let's look into the previous video. We had derived something known as Grubler's cuts back equation. Okay, so if a given system is there, so if n is number of rigid bodies or links, okay, generally we'll assume that one of them will be fixed or grounded. So we'll say number of moving bodies n minus 1 because one of them is fixed. Now we'll also count in a given mechanism. Let's look at 2D case for now. How many lower pairs are there? Okay, so that means joints or pairs with one relative degrees of freedom. Similarly, we'll also count how many higher pairs are there. These are joints with two relative degrees of freedom. Another way of finding out if it is a lower pair is it should have a surface contact. And in case of higher pair, it will have line or point contact. Okay, now let's look into the equation. So what equation we defined was degree of freedom, which is a number, is always given by 3 into n minus 1 minus 2 into j1, number of joints with one relative degree of freedom or lower pairs, minus 1 into j2. Okay, in the previous video I had said if you add this 2 and 1, you should get 3. Similarly, 1 plus 2, you should get 3. So that is a trick so that you don't forget this equation. Okay, now let's look at few standard mechanisms that is typically there. So I have one link like this. There's another link in this manner. There's one more link like this. And finally, there is another link in this manner. Okay. Now, what do you observe? So there are 4 links. Explicitly, if I just have 4 different links, I mean 3 moving links and 1 fixed link, right? So I can label this. This is link number 1, link number 2, link number 3. This is a good practice to have labeling. Now, if I do not put any joint, so for example, I don't have anything here, they are free to move. Okay. So degree of freedom of this particular system will be, this yellow link will have 3 degrees of freedom, the magenta will have 3, orange will also have 3, and the green will not have any degree of freedom because it is fixed. So degree of freedom of this system without any joints will be 3 into n minus 1. Okay, so that is 3 into n is 4, 4 minus 1 is 3, 3 into 3 is 9. That means 3 plus 3 plus 3 is 9. That is clear. Now what we do is we'll introduce revolute joint. Revolute joint allows relative rotation between 2 links. I can have this kind of motion. Similarly, there is a revolute joint here and a revolute joint here. A very good practice is to label the links and label the joints. It is very important to avoid any problems. So I'll label this as R12, revolute joint between link 1 and 2. Similarly, there is a revolute joint between 2, 3. There's a revolute joint between 3, 4, and there's a revolute joint between 1 and 4 or 4 and 1. So typically we'll write it as 1, 4. So what did we do? Once we introduced joints, so we have to do the counting. Okay, so n minus 1 is 3, or n is 4 rather. Let me put it that way. Typically this is how we solve any problem. N minus 1 is 3. Now we'll also count how many joints are there. J1, number of pairs or joints which allow one relative degree of freedom, or number of lower pairs. We have 1, 2, 3 and 4. Okay, so J1 will be number of lower pairs or number of joints with one relative degree of freedom. So in this case, since all are revolute joint, there is no surface contact, sorry, there is no line contact, point contact or higher pair. So I'll write J2 as 0. So degree of freedom, same equation, 3 into n minus 1 minus 2 into J1 minus 1 into J2. We'll just have to write 3 into n was 4, 4 minus 1 minus 2 into number of lower pair is 4 minus 1 into number of higher pair is 0. So this you please do 3 into 3 minus 2 into 4, which is 1. So what it means is we require one parameter, okay, to let's say draw this mechanism. This when we go to GeoGebra, I'll be explaining this in another video. What is the importance or significance of degree of freedom So that will be explained in let's say after a couple of videos. Okay, so the mechanism that we derived just now, there is a specific name for that, so we'll call this as a 4-bar mechanism because it has 4 links. 4-bar mechanism. So right now we'll just understand given mechanism, how do you find degree of freedom. Okay, later we'll also animate them and find out more about them. Now let's look at another standard mechanism that is found in the theory of machines. So imagine I have a coordinate system and there is a grounded link like this, and I can have one link in this manner, then I'll have another link in this manner, and I'll draw one slider. Slider means one rectangular block. Okay, so the idea is this slider can translate within that yellow color groove or slot. Okay, now if I don't have any joints, so let's say this will have 3 degrees of freedom, this will have 3, and this will also have 3, assuming that it can move in all 3 directions. Okay, however, when we introduced joints, so let's say I want to introduce a joint, revolute joint, in this manner. With respect to the ground, I have a revolute joint. Okay. Similarly, there is a revolute joint between the orange and the blue link. There is a revolute joint between the blue and the green. So that means the slider can move, and this is a revolute joint. Now, what is important to also understand is there is a prismatic or a translation joint or motion between the green and the yellow slot. So that is what is visualization of joints. Now let's start doing the part numbering. Now we said something about this guy. So let's say I want to number this as 1. Okay, this white grounded link. This orange, I'll round it as 2. This is 3, and the slider I'll round it as 4. Now the question is, should I make this as 5 or should it still be 1? See, we are looking at rigid bodies. Rigid bodies means they do not undergo any deformation or they don't change their shape. So I can always assume that these two are connected. Rigid. That means they don't have any relative motion like this. So the white and the yellow part. So it is important that we don't consider this as a separate link. It should be same as the earlier rigid body that we have already numbered. Okay. So now let us look at the labeling. So this is a revolute joint. So obviously the revolute joint is between 1 and 2. Rotation between 1 and 2. So there is a revolute joint between 2 and 3. Now this is slightly tricky to understand. That relative motion is happening between 3 and slider. Okay, I need not have to move slider. I can still have this rotation. So this is a revolute joint between 3 and 4. Then there is a prismatic joint or a translation joint, sliding. Now that sliding is happening between green and the yellow. So this is prismatic between 1 and 4. Okay. Now, having said that, so let us look at this. N is equal to 4, n minus 1 is equal to 3. Number of pairs with one relative degree of freedom or surface contact is 3 revolute plus 1 prismatic. So totally there are 4 J1s. Line or point contact, we don't have anything, so this will become C. So degree of freedom, if you calculate using the Grubler's equation, again it will be 3 into n minus 1 minus 2 J1 minus J2 or 1 into J2. 1 into J2. So again, you do the mathematics similar to the FOBA mechanism. Degree of freedom will be 1 for this particular mechanism. So the name of this mechanism is known as slider crank. It's a standard mechanism that is there in the textbooks. Now let's look at a slightly different variation now. So I'll try to create one plus shaped slot. Okay. Imagine there is a slot in this manner. Okay. So I'm going to have a blue color slider in here. Let me try, just to avoid any confusion, I'm going to have a non-square shape there. Okay. Or okay, so I need bigger sliders, so I mean that is why I'm trying to do this. Still same. Okay, it's just that I reduce the size of the sliders grooves. Okay, now I'm going to create a rectangular, slightly longer kind of slider. This can translate and go beyond. It can come till here. Okay, it can go horizontal in the whole slide. Similarly, this one is a green slider. This can go vertical up and down. Okay. Now, obviously, what is the degree of freedom of this system now? I can translate this horizontally, so that is independent. I can also translate this vertically, assuming there is no collision. The degree of freedom of this system will be 2, looking at the system. Now, imagine I have a link that connects them in this manner. Okay, so I'll start giving some joint. So there is a revolute joint here, and there's another revolute joint here. So now let's do the labeling. Again, labeling is very important. So the ground will be 1. The ground is the white one. The blue slider will be number 2. The magenta connecting arm will be number 3. The green slider will be number 4. Okay. So in this case, n is 4, n minus 1 is 3. Now, how many lower pairs are there? So J1 is, there is a lower pair, that is translation. Is a prismatic between 1 and 2. 1 is the white, 2 is the blue. It is translating like this. Out here, there's a relative rotation between the slider that can translate and this link. Okay. So this will become a rotational joint between 2 and 3. Here there is another revolute joint or rotational joint. I'll call it as rotational joint between 3 and 4. The vertical slider and this guy, there is a relative motion. So 3 and 4. Now, is there anything else? Yes, there is one more. The green can slide within that vertical slit. So there is a prismatic joint between 1 and 4. So number of pairs is again 4 here. Prismatic, revolute, revolute, prismatic. We'll have 4. J2 in this case is 0 because there is no point or line contact. So degree of freedom again in this particular case will be 1. So the mechanism that I have drawn is known as double slider mechanism. And it is also, this particular mechanism also is known as elliptical trammel. So in one of the later videos, I'll be covering different inversions of a mechanism. I'll explain what inversions is later. Okay, so we have covered 3 standard mechanism, 4-bar mechanism, slider crank mechanism, and double slider mechanism. Now I'll be trying to take up some more standard mechanisms. Okay, so before that, let me now start drawing in the skeleton method. So by now, you should become familiar that, let's say if I do like this is ground. I can also represent ground in this manner. That is also possible. And typically we'll start, let's say like this, link number 2, link number 3, link number 4. Now I'll also have another link in this manner and connect it with a slider. And that slider, let's say it can translate like this. Now number 4 is done. So this will become number 5, this link, and the slider will become number 6. Now a good practice is to identify the joints. So there's a revolute joint. It is allowing rotation between 1 and 2. I'll call it as 1, 2. There's another revolute joint between 2 and 3. 2 and 3. This guy is between 3. Okay, I'll come back here later. So this particular joint is between 1 and 4. So there's a revolute between 1 and 4. How about this? There's a revolute joint here. It allows relative rotation between 5 and 6. So I'll call it as revolute between 5 and 6. There is a translation possible between 6 and this is 1. So there's a prismatic or translation between 1 and 6. Now please focus on this guy here at the top. So basically 3, 4, 5. So 3 links are intersecting. So if I temporarily assume that 3 is the reference, with respect to 3 I can move 4. With respect to 3 I can also move 5. But when I have moved 4 and 5 to particular angle, the angle between 4 and 5 is already known to me. So that means there are 2 relative degrees of freedom, or 2 relative, I would say, 2 independent angles can be measured. So if I measure this angle and if I measure this angle will be known to me because it is a function of these two. So that means I can assume that there are two revolute joints at that particular location. What are those revolute joints? I'll say 3 with respect to 4 and comma there is one 3 with respect to 5. I could have chosen 3 4 3 and 4 5 also. That is also possible. We'll have to consider one as the reference and the other is, let's say, dependent. Okay, I think we'll follow the same drill. So n is equal to, in this case, 1 2 3 4 5 6. N minus 1, sorry, n minus 1 is 5. J1, number of lower pairs or joints with one relative degree of freedom. So please count 1 2 3 4 5 6 7. Okay, so many a times people miss this out. So J2 is 0. So degree of freedom, again, if you calculate, it will be 1. That means one parameter is required to animate this mechanism. That is what it boils down to. Now let's look at some more examples, standard ones. Later on, we'll also try to say something else. So imagine I have a combination of slider cranks. There is one slider crank in this manner, okay, and I connect another slider crank in this manner. So that's it. So this is a situation given to us. So what do we do? We'll start with grounded. So this is one. I'll use, this is fine. Number two. Now this is one link. I'll call it as number 3. This is a slider. I'll call it as number 4. Here it will still become number 1, the ground, because they are connected. Now the other side, this link is independent. I can move like this. Okay. So this will be number 5. And this slider will become number 6. This is still number 1, the ground. Now let's label. There's a revolute joint between 1 and 2. 1 and 2. I'll come here later. This guy is a revolute joint between 3 and 4. There's a prismatic joint between ground and slider, that is 1 and 4. I'll come here. There's a revolute joint between 5 and 6. And there is a translation joint between 1 and 6. Now here, similar to the 4 bar, whatever we had. So there are, with respect to this blue link, I can move 3. I can also move 5. If these two angles are known to me, this angle will be given. Basically, I can do addition of all these three should be 360 degrees. If this is given, I'll be able to find this out. Okay. So that means relatively two angles are required. So I'll call it as R2 3, comma R2 5. Two revolute joints are there at that particular location. Sometimes it is also known as a binary joint, but I don't want to get into the complication. It is just that it's a different way of telling things. Again, n is equal to, we had 6. This is the last link. Obviously, n minus 1 is 5. J1, we'll have to count. We counted 1, 2, 3, 4, 5, 6, 7. So J1 is 7. J2 is 0. And using the Grubler's equation, we'll find degree of freedom again as 1. That means if I just give this angle, later we'll see, I'll be able to find where are those locations. Okay. After that, let's take another example, another standard. I have a vertical grounded link. Let's use white for ground. And I'll have a link in this manner. Space. I'll have a link in this manner. Then I'll have a slider, and this rectangular block is going within another slot which looks like this. Okay, so and what happens is there's a revolute joint in this case, there's another revolute joint here, and there's another revolute joint here, like this, with respect to the ground. This magenta link can kind of oscillate like this. Now let us try to label the links. So I'll label this as number 1. This yellow one I'll label it as number 2. The magenta, the blue one will be number 3. The magenta one is number 4. So there are 4 links. Okay. Now let's try to understand what are the kind of motions that are possible. So here I'll have revolute between 1 and 2. This one, so please remember the slider is there, so I can have relative rotation between 2 and slider 3. Okay, so this particular location is relative rotation or revolute joint between 2 and 3. Now, if this slider is going along the magenta link, so there is a relative translation possible. So that relative translation is prismatic. Relative means this one is different. Okay, don't get confused. That is from the top diagram. Okay. So there's a prismatic between relative translation is happening between 3 and 4. 3 and 4. Now finally, there's a relative rotation between ground and 4. So I'll call it as 1 and 4. So number of links is 4. N minus 1 is 3. Sorry. J1 is there are 3 revolute joint, 1 prismatic joint, 4. J2 again will be 0. So degree of freedom in this case will be again 1. Okay. So the mechanism that I have just explained is usually known as quick return mechanism or crank slotted quick return mechanism. It's part of a quick return mechanism. I'll just extend that in the next diagram. Okay. So what do? We'll just extend that mechanism with something else. Same diagram, whatever I had drawn earlier. It's just that at the tip of this link, I'll have one more joint and I'll have a slider and a ground. So let's do the same. Number 1, number 2, this is number 3, this is number 4. I'll consider this as number 5 and number 6. This is still number 1. Now let's look at the joints. Again, this is a good exercise. We should have this habit. R12 relative rotation. This is R23. There's a prismatic between this is P between 3 and 4. There's another revolute here between 1 and 4. This guy, there's another revolute, rotational joint between 4 and 5. And here, similar to the slider crank mechanism, 5 and 6 revolute, and there's a sliding is possible between 1 and 6. Again, n is equal to 7, sorry, n is equal to 6, n minus 1 is 5. Number of lower pairs is, the maximum what we have is 1, 2, 3, 4, 5, 6, 7. So J1 will be 7, J2 is 0, so degree of freedom is 1. See, most of the useful mechanisms that we find will have 1 degree of freedom because it is easier to control uh, degree of freedom with 1. Now let's look at another example of a slightly different manner. So imagine I have another mechanism which looks like this. Okay, so we'll quickly do the labeling. This is number 1, ground. This is number 2, number 3, link, number 4, number 5. Okay, now let's look at the joints. This particular joint is R1, 2, rotational between 1 and 2. This is R2, 3. This is R3, 4, R4, 5. Again, we'll come back R1, 5. Okay, so degree of freedom for this is n is 5. 5 links are there. N minus 1 is 4. So how many revolute joints are there? There are 5 revolute joints. J1 is 5. J2 is, there are no line or point contact. J2 is 0. So degree of freedom in this case is 3 into n minus 1 minus 2j1 minus 1j2 is 3 into 5 minus 1 minus 2 into 5 minus 1 into 0 is equal to 3. 5 minus 1 is 4, minus 2 into 5 is, what it means is, if I give the value of this angle theta 1 and let's say this angle theta 5, I'll be able to draw this mechanism. That is what is the big picture. Okay, so I still have to cover the spatial mechanism, degree of freedom. Let me try to save this and start a new. This is 6, I think. Okay, 6, 1. Let me get a new file. Okay. Now let's try with mechanisms with higher pairs. So this seems to be a longer video, but I think it's worth. Let's say I have a gear kind of system. Okay. So I can rotate this gear, and there's another gear which is let's say, okay. So there's a point contact happening here if this guy is rotating. Okay, if this is input, generally what will happen, if this is input, it will mesh and this will become output. So common sense says if I rotate this, this will rotate. So that means the degree of freedom of the system should be 1. So let's try to derive that. So there is a ground. This is the ground, white. Similarly, there is a ground here with respect to which the disks are rotating. Now, The first input gear, I'll call it as number 1. The output gear, I'll call it as part number 2. How many joints does it have? There's a revolute joint between 1 and 2. Sorry, did I call this? Sorry. It should be 2 and 3. My bad. So yellow is, let's call it number 2. Blue one, we'll call it as number 3. Okay. So there is a first revolute joint between ground and link 2. Then we also have a revolute joint between ground. This is number 1, 1 and 3. Now these are lower pairs. Now, if you observe when the gear is meshing, there is a point that is touching the yellow and the blue. So the contact is point contact. So at this location, there is a point contact. If you are looking at 2D, if you have an extrusion, that means 3D. So along the point, there will be a line. So then it will become line contact. That is what it means. So I have a point contact, which is basically a higher pair. Okay. So the good part is now we'll look at n is equal to 1, 2, 3. Only 3 are there, unlike the previous samples. N minus 1 is 2. J1, number of joints with one relative degree of freedom is 2. That is 2 revolute joints. For the first time, we have looked at a point contact, that is higher pair. How many we have? We have 1. So degree of freedom is given by 3 into n minus 1 minus 2 into J1 minus 1 into G2. Okay, 3 into n minus 1 is 2 minus 2 into 2 minus 1 into 1. So 6 minus 4 minus 1 is 1. So degree of freedom, as we said, it is 1 for this particular case. So similarly, I would suggest you to go through something known as cam follower. If this is a cam, if there is a point contact here and there is some form of translation possible. So when I rotate this, this will go up and down. Okay. Again, there's a revolute joint here. There's a prismatic joint here. There's a point contact. Similar to the previous. So degree of freedom of this cam follower shall be 1. You can do the same steps. Exactly same numbers will be there and degree of freedom can be determined. Okay, now let's take an example of some spatial mechanism. Okay, very rarely we use spatial mechanism in undergraduate courses, but it is good to know spatial mechanism. Okay, one of the common mechanism is something known as 6 DOF Stewart platform. This is used for driving simulators, truck driving simulator, helicopter or aircraft driving simulator. So there will be a cabin that will be kept and you achieve all 6 motions using this platform. So typically it looks like this. There will be a hexagonal base. There will be another hexagonal moving platform and there will be, let's say, spherical joints. Spherical joints is that ball and socket joints on this. Similarly, there will be spherical joints on the base. Okay, then we'll look at a set of links which comes like this. I have to go behind this side till there, till here. So there is this be till here, this will be till there. I mean, you'll have to understand this through some other video. I'm just trying to make a skeleton diagram. And which other color can we use? Okay. So imagine there is a kind of a shock absorb kind of thing, prismatic, or I would say cylindrical, prismatic, and rotation possible both. So shock absorbs in a typical two-wheeler, you can assume that there is translation possible between them. This guy will come to the front, this will go to the back, this one also. Okay. Now in this particular mechanism we will ground the base. Okay, so how many links will you see then? There are six blue, six orange, and one green at the top. So n will be one ground, one moving, 2 plus 6 plus 6. How much is that? 6, 6, 12 plus 4, 14. Okay. Now, how many joints are there which allow one relative degree of freedom? So since the joint here, say for example, this thing, these are all having 2 degrees of freedom because there is a relative translation and also it can rotate like this, cylinder inside a cylinder. Okay, so we'll have J1 will not be there. We don't have any revolute joint here. There are J2 will become 6 legs, so therefore 6. Now what are J3? Pairs that have 3 relative degree of freedom. See, my arm, I can rotate in 3 directions. Okay, that is called a spherical joint. So I have spherical joints here as well as spherical joints here. So this is 6 plus 6 is 12. Now degree of freedom, if you remember, it is 6 now because it is a spatial system. It's important we draw this diagram. It's a spatial system. 6 into n minus 1 minus 5j1 minus 4j2 minus 3j3 minus 2j4. Again, you should add them up. j5. Now 6 into 14 minus 1 minus 5 j1 is 0, 4 j2 is 6 minus 3 into 12 and other things are there. So 6 into 13 minus 24 minus 36. Will this be 13 into 3 is 39, 78. Okay, I think that is correct. 78 minus 20, 24 plus 36 is 36, 60. Okay, I think somewhere did I make a mistake? Let's see, what is the degree of freedom we'll get? We'll get 18. So where are those motion? I should get 6 actually. 6 plus 6, 12 I should get. Somewhere I made a mistake. Where is it? 3, 12, 4 into J2s. How many J2s I have? 16 I have. N is 14. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. Correct. Okay, so I'll have to check where I might have made a mistake. So typically in this particular mechanism, degree of freedom will be 6 for translation. That means in the cylindrical, and I can also have 6 rotation. That means the cylinder, if I rotate, it will not have any effect. So totally, I think it should be 12. I'm not sure where I made a mistake. But anyway, special mechanisms are usually complicated. So let me see in one of the other next videos, I'll try to clarify this. With that, I would like to conclude this. Thank you very much.